In this lesson, we're going to discuss the application of calculus to work in physics. So let's first give the technical definition of work used in physics, and we're going to talk what the work units are in the metric system and the US customary system. So the definition is this: if an object is moved in a distance d in a direction of a constant force F, the work is force times distance. Work is W equals force times distance. And generally speaking, if you hadn't had physics, this is a little bit tricky, but force is the push or pull on an object. And here we're going to talk about, say, metric and US customary second. Metric and then us. So in the metric system, force is given by mass, usually in kilograms, times acceleration, which would be given by the second derivative, so d squared s over dt squared, where s of t is some position function. Often what you use for d squared s over dt squared is acceleration due to gravity, so I think that they typically use 9.8 or 9.81 depending on the situation. And so in metric, work is this force times distance, and so that would be have units. It'd be m times d squared s over dt squared times d, and this is usually measured in kilograms, say meters per second squared, and meters. And holy moly, that's often, sometimes that's called a Newton meter. And the reason that's true is because this force function's units are newtons, or another word for Newton meter is joule. And surprisingly, this is one of the things that is actually easier in the US system. In the US, force is measured in pounds. So typically work being force times distance, force measured in pounds, distance measured in, say, feet. The most common unit is foot-pounds for work. So something else about work is that it's not time dependent. So it doesn't matter if you do something over an hour or a day. If you move something with the same, say, force over the same distance, how long it takes is not accounted for in this definition. So how much work is done in each of the following scenarios? Lifting a 2-kilogram book off the ground to put it on a deck that's 2.5 meters high. And we're going to use acceleration as 9.8 meters per second squared. So work is force times distance. In this case, the force is mass times the acceleration times the distance. So that will be 2 times 9.8 times 2.5, and that will equal 49, and the units here are joules. Remember that the units of the force, as in the 2 times 9.8, that's what the newtons are. How much work is done lifting a 50-pound child 5.5 feet off the ground? So work is force times distance. The force is 50 pounds, 5.5 feet. So that will be 275 foot-pounds. So suppose that an object moves along the x-axis from A to B, and at each point in there, a force F of x acts on that object. And we're going to assume that the force is not always the same. Like suppose that if you're trying to, like, say, pull out a spring, the force required to pull it out will become greater the more and more stretched out that spring becomes. So what we have here is we have some curve y equals f of x. And what this curve describes is the curve of the forces. And so when I plug in a particular x value, that tells me the force required to move an object like a little distance at that point. So the first thing that we do, we want to find the total force to move the object from A to B by adding up all of the forces. The first thing you do is you divide AB into little subintervals, so into n pieces, and then we'll have width delta x equals b minus a over n. You pick a sample point, and the force at that point, so force at the sample point, we're going to call that sample point x sub I star. Samples always have stars. And the force will be f of x sub I star. Like, you plug that number into the function, it tells you what the force is. And so the work to move from that little bit, so work for an ith piece, will be the force times the distance, which is delta x. And so your total work will equal a limit as n goes to infinity of all these sums, all these pieces added together, which is actually just going to end up being an integral from a to b of f of x dx. And I think if you think about it as you take and add up all of the forces, that should help you. So we're going to have to find an equation for what the force is and then integrate from where we start to where we end. And so the hardest thing is figuring out the equation for the force. So first let's just suppose we're given a dummy force equation. So we know when a particle is located x feet from the origin, this is the force that acts on it. How much work is done from moving it from 0 to 2? So you find the work by adding up all the forces. 0 to 2, x squared plus 5x dx. So that's 1/3 x cubed plus 5 over 2x squared. 0 to 2, so 8/3 plus 5/2 times 4, which is 8/3 plus 10, or 38/3. And to think about what the units are, think about this. You have the x-axis, which is feet. You have the y-axis, which is pounds. And that can be another way to convince yourself that the area underneath this curve is foot-pounds. So 0 to 5 foot-pounds. And that problem looks something like this. At least the area underneath the curve has the appropriate units for it to have the units of work in the US customary system. Now, one common application of work in physics and in this class will be the force required to move a spring. And so Hooke's law says that the force required to maintain a spring that's stretched x units beyond its natural or resting length is proportional to x, or proportional to the distance, meaning that you have this kind of equation where k is a positive constant and x is not too large. So meaning you don't overstretch your spring. And this constant k will vary depending on how tough it is to stretch your spring. So a force of 12 pounds is required to hold a spring stretched 3 inches beyond its natural length. How much work is done in stretching it from its natural length to 6 inches beyond its natural length? So for springs, the force is given by a constant times x. And before you can proceed, you've got to figure out what the particular constant is for your particular case. So we know that f of x equals 12 when x equals 3 inches. Now, since force is usually measured in foot-pounds in the US customary system, let's make this inches into feet. So 3 inches is 3 out of 12, or 1/4 of a foot. So using the fact that our force is 12 pounds when we are a 1/4 foot away, we know that f of 1/4 has to equal 12, or 1/4 times k has to equal 12. Therefore, k is 48. And our force equation is 48x. Then we add up all the forces, the work done. So to stretch it 6 inches beyond its natural length means we start at 0, we end at 1/2 because we've changed our units to be feet, and we integrate 48x. So add up all of those forces and we get the work. So 48 divided by 2 is 24. So that's 24 times 1/4, or 6. And the units here would be foot-pounds. If you did not change the inches into pounds, what you're going to get is 72 inch-pounds. But pretty sure things like WebAssign would require that you convert that, which you could just do by dividing by 12. Like, that will work. It's just a matter of remembering to do so. So this next question is a bit tricky, and it turns out that part A is much harder than part B, so just be aware of that. Suppose that 4 joules of work is needed to stretch a spring from its natural length of 30 centimeters to a length of 40 centimeters. So here's the one tricky thing. 30 centimeters corresponds to resting, or 0. 40 centimeters corresponds to 10 centimeters, or 10 centimeters past rest. So in that Hooke's law equation, x is how many distance past rest. And you want to know how much work is needed to stretch it from 35 to 40. So first of all, you need to find the k, but you know the work, not the force. So your work is equal to the integral of this kx equation from 0 to, well, we need to do meters here, so 0 meters to 10 out of 100, or 0.1 meters. So that, and we know the work is 4, so 4 equals, well, k over 2x squared, evaluated from 0 to 0.1. So 8 equals k times, well, 0.1 is 1/10. So 8 equals k times 1 over 100. And you can figure out that, well, 800 equals k. So in this case, your force equation is 800x. And that would be measuring things in newtons. And you want to figure out how much work is needed to stretch the spring from 35 to 40. And so in that case, 35 is, instead of 1/10, it will be 5/100th. So 0.05 to 0.1, 800x dx. So 800 divided by 2 will be 400x squared. I'm going to do 5 out of 100 to 1 out of 10, and 5 out of 100 reduces to 1 out of 20. So 400 times 1 over 10 squared minus 1 over 20, the quantity squared. So 400 times 1 over 100 minus 1 over 400. So that'll be 4 minus 1, or 3. And what you'll notice, that's a little bit interesting, that to go from 30 to 40, it took you 4 joules of work, but it was only 1 joule of work to go the first 5 centimeters and 3 joules to go the last 5, which should make sense that stretching the spring initially is less work, but over time is more work. And part B says, how far beyond its natural length will a force of 300 newtons keep the spring stretched? So we have the force equation is 800x. So we know that the force is 300. And so that's going to give us that 3 over 8 equals x, and that's how many meters? So x equals 3 over 8 meters. Now another application of work is lifting things. So we have this heavy chain, and it's 100 feet long, and it weighs 3 pounds per foot, and it hangs over the edge of a building that is 250 feet high. How much work is done in pulling the chain to the top of the building? So you have your building, and over the side of the building, not drawn to scale, hangs this chain. It's 100 feet long. So I'm going to orient my x-axis here. I'm going to call this 0, and I'm going to orient my axis down. So that's my point. We'll say x sub I. And the thing is that each piece moves up a different distance. So like many other things, we're going to break it up. We're going to try to figure out how much does it take, how much work to move a little chunk. So step 1 is to divide the interval into n pieces. So divide 0 to 100 into n pieces with width delta x equals 100 over n. And we're going to let x sub I be a point in, we'll say, the ith subinterval. It's like x sub 1 would be in the first interval, etc. So the work for moving this little chunk up to the top is going to be the force on that little chunk times the distance the little chunk moves. And that little chunk will be delta x long. So first of all, little chunk weighs 3 pounds per foot. So we have 3 pounds per foot. And for me, it helps to keep track of units. Force is easily measured in pounds. So 3 pounds per foot times we have delta x feet. That tells me how many pounds my little chunk weighs. And the distance little chunk moves is x sub I. And x sub I is going to range from moving none to 100. So the work on a little slice is 3x sub I delta x. And so the total work is equal to a limit as n goes to infinity of a sum of all these things, or an integral from 0 to 100, 3x dx. And once you get the setup, most of these integrals should be really, really easy things. So this will equal 3 over 2x squared from 0 to 100, which ends up giving you 15,000 foot-pounds. All right, what if you pull up half of the chain to the top of the building? So same picture. So there's 100 feet down, here's 50. And you have your chain, and you've got 2 distinct pieces. You've got these pieces that all move different distances, and everything in this piece each moves 50. Like this 100 moves up to 50, the thing that's at 99 moves up to 49, etc. The thing that's right at 50 goes up just to the 0 on the top. So the work here, you have to find the work for the first piece. So the first 50 feet plus the second 50 feet. And so that first 50 feet isn't so hard. You integrate from 0 to 50, same curve as before, so 3x dx. Now for the second one, your pieces start at a distance of 50 down and they end at a length distance of 100 down. Now the force on each piece will be 3 dx again. So remember that this was the pounds per foot times delta x was the feet, so that gave you pounds. And this x in this equation was the distance the pieces moved because they all move different distances. But this bottom part, each piece moves 50, so that's going to be times 50. The distance is not changing. Every single piece moves the same distance. So here we'll have 3 over 2x squared from 0 to 50, and here we're going to have 150x evaluated from 50 to 100. So that will equal 3/2 times 2,500 plus 15,000 minus 7,500, and that ends up being 250 foot-pounds. So the difference between those two is that in this first one, the distance, which is given by that x, is varying, whereas in this one, every single piece of the chain down there only moves 50. And you can think, well, okay, it's a little bit silly. Maybe I'm going to be a mining engineer and I'm going to need to figure out how much work to lift some coal out of a mine. We can do that too. So the cable needs to be accounted for, because if you're going to pull up heavy stuff, the cable will need to actually be heavy as well. So your cable weighs 2 feet per pound, and you're lifting up 800 pounds of coal from a mine shaft that is 500 feet deep. So you have this shaft. It is 500 feet to the bottom. We'll call that 0, call that 500. And the total work is going to equal the work for the cable plus the work for the coal. And it turns out that part's pretty darn easy. That coal part will just be given by force, which is 800 pounds, times distance, which is 500. So on the end, we're just going to have to tack on a huge old 400,000, excuse me. Now the cable will be pretty similar to before. So for the cable, we have little chunks. They're at some exabyte. So the force on a little chunk will be 2 feet per pound times delta x pounds. And the distance for a chunk is going to be exabyte. So the work to move one little chunk will be 2 exabyte delta x. And so your total work for that cable is going to be integral from 0 to 500, 2x dx, and then plus the 400,000 for the coal itself. So x squared from 0 to 500 plus 400,000, which is 250,000. Plus 400,000. Look, that cable was an awful lot of work, wasn't it? So it's a total of 650,000 foot-pounds. And the last thing we're going to do is discuss how to find work when you're, say, pumping something out of a tank. So we have an aquarium, and it's 2 meters long, 1.5 meters wide, and 1 meter deep. So that's 1.5. This is 2, and this is 1. And we're going to pump all of the water out of this tank. And just for simplicity, what we're going to have to do is we can do calculus with this, is we're going to have to think about taking a chunk of water, like a very, very, very thin sheet, and just taking that out to the top. So it's not, according to my physicist friends, it's realistic enough. And if you need to be more accurate, you can do some more special stuff with it. But for now, we're not going to go there. So this is going to be 0. Down there is going to be 1. And the distance a slice has to move is going to be some x sub I. So our work is force times distance. First, we have to find the force. So force is equal to mass times acceleration due to gravity. And the mass will equal the density of the liquid times the volume. And the gravity here is going to be 9.8. Notice that I had to do this because of the fact that I had the metric system. So the density of water is given as 1,000 kilograms per meter cubed. So 1,000 kg per m cubed. The volume of a slice is going to be 2 times 1.5 times delta x, so how thick our slice is. And note that's going to have units meters cubed because it's a volume. And then times this 9.8, which will have units of meters per second squared. And I'm just checking that the units match up what they should be for force here. And notice that those meters cubed cancel. So this, and the units here were newtons. And newtons were kilogram meters per second squared. As weird as that unit is, I'm afraid I can't wrap my mind around it. It's just so nuts. But the units do check out to what they're supposed to be. So this is 29,400 newtons. And the work for a slice will be the force for that slice times the, and also there should be a delta x, excuse me, I shouldn't forget that, times the distance that slice moved, which will be 2,900 x sub I delta x. And the total work will be given as an integral. You add up the slices from 0 to 1. And this integral is pretty simple. And to differentiate, 29,400 divided by 2 will be 14,700 x squared from 0 to 1, which is 14,700. Remember that work is measured in joules. Now, what if you have a tank that has a little bit more complicated shape? So I have a tank that is an inverted point down circular cone with a height of 10 feet and base radius of 5. You thought that cones had gone away, and they hadn't. So I'm going to orient my cone like this. Okay, so this height is 10. I don't know why they say point down and then say base radius, but anyhow, whatever that is, this is supposed to be 5. And we're going to think about, say, taking out slices of water at the top of the tank. Okay, so first of all, we have to find our force. So if that's my random delta x, or delta y in this case, actually, that's my random delta y, the force will be the volume times the density. And we're told that the density is 62.4. So V sub I times 62.4. So you think if you have a cone like this, each slice is going to be a circle. So to find the volume of a circle, you'll need to do pi r squared. And times, of course, delta y. So pi r squared delta y will equal your volume. So you got to figure out what that r is. So what is this r sub I? And to figure that out, you can use similar triangles. So this distance is y sub I. R sub I over y sub I would equal 5 over 10, or r sub I is 1/2 y sub I. So there's the relationship. So our force will be pi r squared delta y, so 1/2 y sub I squared pi 62.4 delta y. So there's the force on one particular slice. So squaring the 1/2 gives us 1/4 times 62.4 is 15.6 pi y sub I squared delta y. Okay, so that's the force. Now the work for a slice is the force times the distance. Now this particular setup, in this setup, the distance is a little bit tricky. So the distance is from here to there, is how far a piece has to move. And y sub I is the distance like up to that first purple dot. So the distance a slice has to move is actually 10 minus y sub I. So think, for example, if your y were at 7, the distance something has to move is 3. 10 minus 7 makes 3. So that is the general work equation. Then you limit becomes an integral, and the total work is an integral from, now notice it says from a depth of 1 foot to 10 feet. So that means that our y's actually range from 0 up to 9. So 0 to 9, 15.6 pi y squared 10 minus y dy. And then it's just arithmetic and a little bit of tedium and patience and calculator. So 15.6 pi integral 0 to 9, 10y squared minus y cubed. So that's 15.6 pi times 10/3 y cubed minus 1/4 y to the 4th, evaluated from 0 to 9, which gives us 12,320.1 pi, and this units will be foot-pounds. So that kind of question is probably appropriate for like a take-home quiz, but probably won't occur on anything in class where you're timed.